Hey everyone, hope everyone is good. On today's session, I want us to look at functions of random variables, which is the beginning of chapter 6. Let me just share my screen. Okay, cool. I want us to look at functions of random variables and then look at how do you find the distribution for these random variables, right? But let me just give you guys a clear background of introduction of this chapter. In statistics, we understand that we have something called a population. Population is everything of the same character, right? Now, since it's difficult to find information based on the population, we often find a sample, which is a subset of the population, right? So a sample, so a sample is a subset of the population, right? What does it mean? It means that it's just a proportion or just a portion from the population. And from chapter 1, you'll remember that everything calculated based on the population is referred as a parameter, right? So your parameters could be either mu, your variance, or your proportion, right? And from a sample, we'll recall that everything calculated based on a sample is referred as a statistic, right? These are estimates. These are called estimate. Estimate. Now, what is an estimate of the mean? It's just x bar, the estimate of the variance of these parameters. Now, for the variance, it's just SD squared, right? And for the proportion, it's just P hat, right? Now, you do all these things, you do everything, right? From getting the subset of the population, you do all this because you're interested in doing what is known as inferior statistics, right? You do all this because you want to inferior statistics. Inferior statistics, right? Inferior statistics. So you do statistics. So your point of doing all this, right? It's because you want to do something referred as inferior statistics. What is inferior statistics? Inferior statistic is a situation where you want to conclude on the sample or given a sample while you infer infer or refer to while you're referring to the population. That's your that's your main aim, right? So whatever information you would find based on the sample, you want to make conclusion based on the whole population, right? And doing so, what you doing is called inferior statistic, where you're concluding based on the sample about the whole population. Now, if you look at the sample, if you look at the sample, all the statistics, statistic, so everything that is calculated here, which is an estimate, is of random sampling, right? So here you have your y1, y2 up until yn, right? So these variables are called random variables. These are random variables, right? Now these random variables, whatever statistic you'll calculate based on these random variables would be subjected. So whatever statistic calculated on the sample will be subjected to n, right? For example, for example, if you look at the statistic like the mean, right, x bar, this is equals to the summation of xi divided by n, right? It's subjected to n, right? Now, this is not just now an estimate. This is also called a function of the mean, of finding the mean, right? This is a function. So chapter 6 is looking at these functions, is looking at all the functions of random variables, all the functions of random variables. So these are the functions, right? So all the statistic functions of random variables. This is what we're gonna look at. And what are we interested on? We're interested in in finding the distribution functions, the distribution, sorry, of these random functions, right? The distribution. So we're interested in finding the distribution of these random functions, right? So why are we interested in finding this distribution of these random functions? It's because from one population, you can have multiple samples, right? From one population, you can have multiple samples. So what we're trying to do is sort of have a general form of the distribution of these samples, right? The distribution of different samples that you might find from one population. Because if we know the distribution, meaning capital letter F of Y, it's easy for us to, so this is general. So if we know the general distribution, it's easy for us to know the probability density function, because we know from chapter 4 that if f of y is given as just an integral from minus infinity to y, f of t dt, then we know that if we can find this, then we know that f of, so small letter f of y, right? It's just the derivative of the distribution function with respect to y, where this is the PDF, right? What else do we understand? We also understand that if you have from a sample, right? We also understand that if you have random variables, so y1, y2, up until yn, we understand that these variables are independent variables. Now, if we understand that these are independent variables, what does it mean? It means that the probability of y1, y2, up until yn is the same as the probability of y1 multiplied by the probability of y2 multiplied by up until the probability of yn, where 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 y1 up until and y2 up until yn are discrete random variables, right? Random variables. Random variables, right? So what does it mean for continuous variables? Still the same thing. The probability of y1, y2 up until yn is just given as f of y1 multiplied by f of y2 up until f of n, right? A probability of f of n, right? Probability of, sorry, just f of yn, right? Right. Where this is true if your y1, y2 until y3 until yn, these random variables are continuous random variables. Random variables. So this is true, right? Okay. Now let's look now at how do you let's look at how do you find, so finding the probability distribution of U functions, U functions of random variables, right? Where U is a statistic function from the sample, right? Like an example of it will be your x bar is equal to the summation of fi divided by n, right? So this could be your U, right? So these are functions. So these are functions. These are your functions, right? Right. So now let's consider random variables, y1, y2, so yn, and a function u, which is a function which is subjected to these random variables, right? So you u into y1, y2, up until yn, right? And we denote this function as u. Okay. So we're trying to find what? The probability distribution. Remember, what is a probability distribution? From chapter 4, probability distribution is capital letter F of Y, right? But now we're not speaking about just one variable, which is Y, but we speak about a function which which is subjective of these Y variables, right? So what we're trying to find here or trying to learn today is that we're trying to find F of U, right? Capital letter F of U, the distribution function of these U functions, right? Probability distributions of U, right? Now to do that, there are three methods. There are three methods for finding U, this distribution, right? This distribution. There are three methods of finding this distribution U. So the first method is the method in 6.3, right? Which is the method of distribution functions, right? Now, what do I mean about finding U? I mean finding like the PDF of U, right? The PDF of U. There are three methods you could do this. Is either through the distribution function, or you could find this using the method of transformations, or you could find this probability density function using the method of moment generating functions. But in today's session, we only going to look at this method, right? The method of distribution function. The method of distribution function. Right. So what do we know? Maybe make this a bit bigger. Right. What do we know? What do we know? Right. Let's see, what do we know? If y has probability density function f of y, right? And if u is some function of y, right? You remember that we said u is subjected to these y variables, right? Random variables. Okay. So this means that, okay? Then if y is subjected if u is subjected to all the random variables y, and we know that the identity function of y is f of y, then then we can find f of u, right? Distribution function of u is equals to probability of u less than small u, right? Directly by integrating f of y over the region over the region for which u is less than or equals to small u, right? So we all understand that the distribution function of y is capital letter F of y. This is the same as the probability of y less than or equal to small y, right? So if we know that u is subjected to y random variables, then this makes f of u to be just u less than or equals to small u, right? Since u is subjected to y random variables, right? Then, if let's look at an example to see how we could go about this. But before we also look at the example, we understand that the derivative of this function, so the derivative of distribution function f of y is just equals to the identity function of f of y, right? What does this mean then? This then means the derivative of f of u is just the identity function of u small letter f of x, right? This is the PDF, right? This is what we want. This is what we want. And why is this important, right? This is important. Obviously, we're trying to find the general format of the distribution functions of all the sample, the subsets that you could find, the sample, which is the subset of the population, right? So we're trying to generalize all the distribution of those samples, which will be the subsets of the whole entire population, right? Because if we have this, it's going to be easy for us to know the expectation of you, to also understand the variance of you, right? Where these will be now estimates of the population. And the reason we also do this, we're trying to also make sure that we don't get a bias estimate. Because if we get bias estimates, it means that our conclusion will also be biased. Now remember, if you have a population and different people take different samples and make different conclusions, some of the samples here might be biased. But if we generalize all these sample and find the general format of representing all the subsets, all these subsets from the population, which will be your samples, it makes life easier to minimize the biasness of these estimates. Okay? Right. So now let's look at an example. Example 6.1. Right? So this is an example I want us to look at. Okay, 6.1, right? So this, let me just uh hmm, not you. So example 6.1, right? Okay, good. Now, right, so this is the example. So a process for refining sugar, so for a process for refining sugar yields up to 1 ton, right? For pure sugar per day, but the actual amount produced, Y, is random variable because the machine breaks down and other times it slows down, right? Suppose you're given a Y density function given by this, right? I want you to find, so it's this. Let's look at, right? So you're also being told, that the company is paid at the rate of $300 per ton for the refined sugar, but it also has a fixed overhead cost of $100 per day. Thus, the daily profits in hundreds of dollars is this. So if you look here, you're given function of U, right? Which is subjective to Y. Now they want you to find the probability density function for U. So they want you to find the PDF for U, right? Now, obviously, what you need to understand, for you to find the PDF of U, you need to know the distribution of U, right? What do you do then? You say, this, you know that f of U is equals to the probability of u less than or equals to small u, right? This is the same as the probability of 3y minus 1 less than or equals to u, right? If you make y the subject of the formula to make your life easy, then you'd have the probability of y less than or equals to u plus 1 all divided by 3, right? Then how do you then find this probability? So to find the probability of y less than or equals to u plus 1 divided by 3, you look at the intervals of y, right? So if you look at what you're given, so y is from greater or equals to 0 but less than or equals to 1, right? We could just see that from here. Now, if you want to find this should be an integration since you could see that this is a continuous variable from the interval itself, right? So it's not the summation, but the integration. Now, the integration from where to where, right? You remember very well that um you remember this, right? You remember, so let me just refresh your memory here, right? You remember that f of y is equals to the probability. So this is chapter 4, right? F of y is equals to the probability of y less than or equals to small y, right? Which then this is equals to the integration from minus infinity to y f of y dy, right? Right? Now, what does it mean? So you come here now. So to find now this, you need to see where does your y start. So my y start from 0 also by looking at this, right? You could see that y, because of less than or equals to, will start from 0. This is like will be the upper bound of y, right? In our case. So u plus 1 divided by 3, right? Multiplied by the density function of y, which is 2y. 2y dy, right? Then, once you understand that, you do your integration. So then this should be just what? Y squared. You're integrating from 0 to u plus 1 divided by 3, which then this will be just equals to u plus 1 all squared divided by 9, right? And you do understand that um, your interval for y is greater or equals to 0, but less than or equals to 1, right? And the your u is equals to what? Your u is equals to so if you look here, your u is equals to 3y minus 1. So it's 3y minus 1, right? So you want to sort of find the interval of u now. So the interval of u then should be, say, multiplied by 3 both sides. It's gonna be 0 less than 3y times 1 times 3, right? Times 3. Then you minus by 1 because you want to make, or you want to find rather, the interval for u, right? If you minus by 1, so this becomes u, this becomes minus 1, this then becomes 2, right? So what does it mean? So your distribution function for u is u plus 1 close bracket, all squared divided by 9, and the interval is this, right? So if you want to have like a complete definition of this distribution, this should be just f of u being equals to the 0 if if you're looking at u less than minus 1. There is no distribution function for anything u less than -1, looking at this, right? Then we know that for u greater or equals to -1 but less than 2, you have u plus 1 divided by 9 all squared. This should be just u greater or equals to -1 but less than or equals to 2, and 1 if your u is greater than 2, right? This is by definition of the distribution function, that the first distribution function um, from negative infinity, if you remember the properties of distribution functions, should be 0. And as y goes to infinity, the distribution function should add up to 1, right? Now, once you understand that, then how do you then find the the density function now? Because that's like the actual question, right? The density function, the density function now is just the derivative of f of u, right? Distribution function. So f of u then becomes what? The derivative of 0 is 0. The derivative of 1 is 0. So, but the derivative of this is 2, right? So it's 2 u plus 1, right? Divided by 9, multiplied by the derivative of the inner function, which is u plus 1, which is just 1. So this will then be 2 over 9 u plus 1, right? Where you know that u is between -1 and less than or equals to 2, right? And 0 elsewhere, right? So this is what you want, right? Let's look at other example, that are picked up from exercise 6.2, right? Let's look at these other examples to see if we do understand this, right? So we're doing exercise 6.2, right? So 6.2, let's see if we have it here. Okay, 6.2. 6.2 is it you? Okay. Can't we make this image? Yes, this is 6.2 exercise. Let me just erase here. Right. So this is 6.2, right? If you look here, you've got this density function. Let y be a random variable with the density function given by, right? Okay, where you also have an interval of y being greater or equals to -1, but less than or equals to 1 and 0 elsewhere. Now, what are you interested on? You're interested in A, right? Find the density function of u1. In this case, u is just 3y, right? What do we know? We know that f of u is the same as the probability of, so density functions are PDF, right? We want to find that, the PDF of u, right? But we know that this is the same as saying probability of u less than or equals to small u, right? Then this is the same as saying u as being 3y, right? It's less than or equals to u, right? What does it mean? It means So to make y the subject of the formula, this is the same as just y less than or equals to u divided by 3, right? We do understand that remember, f of y is the same as minus infinity to y f of y dy, right? We do understand that. So what does it mean? It means for us to find this distribution, we need to see where does our y start. It start from -1, right? So the probability of y less than or equals to u over 3 then should be the same as saying you're starting from -1, but your endpoint should be just u over 3, right? Then you take the density function given to you as equals to the density function given to you is equals to what? Let's see. It's just 3 over 2 y squared, right? So it's 3 over 2 y squared, which is what you given, right? And you want to find an integration of this with respect to y. Now, if you find now the distribution of this, you should know that this should be just what? This should be just what? Um, this should be just an integration um of so you take 3 over 2 this side, then the integration here is just y. It's y cubed divided by 3, and you're integrating from -1 to y over 3, right? Y over 3. And so this then becomes what? This becomes 3 over 2. This just becomes if you look here, 3 multiplied by 2 is 6, right? So this is 6, right? Then you have u cubed over 3, right? Minus now -1 cubed, right? Okay, we good? Yeah, so -1, right? So this then now changes from 3 over 6, where 3 over 6 is the same as half, right? This is the same as half. So this is the same as saying 1 over 2, right? Where now you have u cubed over 3 squared. 3 squared is equals to what? 3 squared is equals to, what is 3 squared? 3 cubed, rather. 3 cubed is it not? It's 9, right? 3 cubed is 9, right? So if you say now, no, we made a mistake here. 3 cubed is not 9, it's 27, right? So 27, right? Then minus the cubed of -1, it's just -1, right? So this then becomes 1/2 of u cubed over 27 plus 1, right? Which then means 2 times 27 times 2. I think we made a Did we make a mistake somewhere? Let me just see something. Okay, let's continue. Let's continue. So this will be just 1/2 of u cubed over 27. So let's multiply this 27. So 2 times 27 is 54. So this is now 1/54 of u cubed um, plus 27. Because what I've done here is say u cubed over 27 plus 1 is the same as saying um uh u cubed plus 27 over 27, right? Okay, right. So this is our final form of what? Of f of, so this is f of u. This is f of u. But if we want to find now f of the density function of u, it's just the derivative of this, right? So if you look here, the derivative of this will be 0, right? So we only have this to derive. So it should be then, so this should be just 3/54 u squared. The derivative of this, that is 0, right? So then the derivative just becomes u squared over 18, right? Because 3/54 is 1/18, right? Which is what you're being asked to find, right? Then you need to now also state the interval of u, right? So you've got y, you're being told that y is between -1 and 1, right? But now u, the function of u is 3y. So you multiply everything by 3, then you'd have -3 to 3, which then this 3u becomes, this 3y becomes u, okay? Now, this is one way of doing this. Another way of doing this, because you're given a density function of y, right? So another way, so second method to find the answer, right? So the second method to find the answer, because you given the density function of y, we know that probability of u less than or equals to u is the same as probability of 3y less than or equals to u equals to probability of y less than or equals to u over 3, right? We know this is the same as the distribution function of y, right? With respect to just u over 3. So what does this mean? It means that we could actually find the distribution of y if that like is an easier method for you. Find the distribution of y, which will be from minus infinity to y, f of y dy by definition. So then this will then be from -1 to y of the density function given to you as 3 over 2 t squared dt, which then this will be just 3 over 2 into just t cubed over 2, you differentiating from -1 to y, right? Sorry, this should be, but it's one and the same thing, but it should be um, f of t dt, right? Then um, to integrate, so we're integrating. So to integrate there, you would have 3 over 2 into y cubed over 2 minus 1 over 3 over 2, close brackets. This will then just be 3 over 2 of y cubed over 2 minus 1 over 3 over 2, right? This will then give you the distribution function of y as just being equals to half of y cubed minus 1, where we know that y is between -1 and 1, right? So if then we want to find f of y u over 3, this will then if you find f of y u3 u over 3, then we could sort of differentiate here to find f of u, f of u, so the density function of u, right? F of u, right? So because now we have this, what is the derivative? So so f of u over 3, this then becomes half of u over 3 of 3 minus 1, right? Which is what we had on my previous method, right? So then this means f of u we know is just the derivative of u, this distribution function, right? Which will also give you just u squared over 18 under the same interval -3 and 3, right? So I want you to try B. Okay, now let's look at another example. Let's look at another example. Let's look at another example. Right, maybe before we look here, before we look at this one, let's look at this example. Uh, Right. Let's look at this example now. Example 6.2, right? So we'll come back to this one. Just put it there. Let's look at this one now. So this is example 6.2, right? So in this example, 5.4, we considered a random variable y, right? Which is the proportion amount of gasoline stocked at beginning of the week. So y1 is the stocked gas, right? Y2 is the sold gas, right? Now, so the joint density function you're given is this, right? Now find the probability density, so the PDF again, right? PDF again. The density function of for u, but now u is of two variables. So u is no longer just y, but it's y1 minus y2, right? The proportion amount of gasoline remaining at the end of the week, right? So it's y1 minus 2, which makes sense because the amount of petrol you've poured minus the amount of petrol you've sold should give you the remaining amount in a week, right? And we know that Y2 should always be less than Y1. You can't sell more than you've poured or more than you have, right? So they want us to find the density function of U and the expectation of U, right? Now, before we then focus on this, so let's maybe model it. So f of u, so now we know that f of u is equals to the probability of u less than or equals to u, which is just probability of y1 minus y2 less than or equals to u, right? Um, then Then, if you want to make y1 the subject of the formula here, it should be y1 is just less than u plus y1, right? Plus y1, right? So this is a double integration problem because you have two variables, but you need to um let's look at this example here before we go finish off that one, right? We need to understand something here, right? So in this example, which is 5.6, right? You want to find the probability of y1 minus y2 being greater or equals to 0.5. I'm going to say greater or equals to because I'm dealing with the continuous variable. So it's either way, right? Greater than or greater or equals to is still the same thing, right? Now, to do this, I know that I need to do a double integration of my identity function f of y, which is this 1 and dy2 dy1, right? 1, 2, right? Then how do I find these intervals? Now, if you look here, right, and you're being told, okay, you're being told, yes, you're being told that y1 is greater or equals to 0, less than 1, but y2 is also greater than or equals to 0, but less than 1, right? So if you look at here, your region, the region where you want to find the probability, it's y1 minus y2, right? You want to only find the probability where both these regions subtract each other but greater than equals to 0.5. So if you make y1 the subject of the formula here, this then just becomes um this becomes so y1 it's then going to be greater or equals to 0.5 plus y2, right? So just from looking at this, right, you could see that y1 starts from 0.5 plus anything y2, right? Just from this, because greater than, right? So I'm starting from 0.5 to um wait to 0.5 plus y2, but I know that this should be less than or equals to 1, right? So my upper bound from what I'm given to y1, right? I know this should start from 0.5 up until 1, right? So I always try to make the first integral to be of constant, then all the variables would be on my second integral, um, which will be my second interval, so y2, right? So then if this is the case, what is y2, right? So if you look at, so now let's make y2 the subject of the formula. So minus y2 um um less than um so minus y2 greater or equals to 0.5 um plus, so minus rather, y1, right? So if you divide both sides by negative, then you'd have y2 less than or equals to minus negative 0.5 plus y1, right? This I could also represent it as, say, this is just y1 minus 0.5. So from looking at this, now what does this tells us? It tells us that the 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 intervals of y2 start from 0 because it's less than, right? So it means then y2 starts from 0, but its endpoint is y1 minus 0.5, right? So y1 minus 0.5, right? So this is how you solve this, right? So because I know this now, because I know this, I need to come back here and say, so if you want me to find the probability, so if you want me to find, let me just minimize this to just make sure. So if you want me to find this probability here, right? So let me erase this. You want me to find so if you want me to find this probability of y1 minus y2 less than or equals to u, right? But I know that this can be the same as saying 1 minus, so I'm taking the advantage of understanding the distribution. 1 minus probability of y1 minus y2 greater or equals to u. The reason I'm doing this, it's because I remember 5.2, how I saw 5.2, which wanted me to do like this, right? Now, with that understanding, then, so what does this mean? It means that this is just 1 minus the double integration from u up until where? So you're being told here that y1, right? You're being told that y1 is greater or equals to y2, but greater or equals to 0, but less than or equals to 1, right? So you're starting from 0 up until 1 again, like how you did in 5.2. Then that means, and so for interval y2, then you'll start from 0 to y1 minus u3 y1 dy2 dy1, right? So if you look at this, then so you do the integration now. You start with an inner integration, then the outer integration. So this is inner, this is outer, right? How do you do that? So you need to say 1 minus an integration from u to 1 of so this is just so you're integrating the inner now. This will just be 3y1, y2. You're integrating from 0 to y1 minus u d y1, right? Which then this should then give you this should be just 1 minus the integration from u to 1 of 3y1 into just y1 minus u d y1, right? So now let's integrate with respect to y1, right? This should be just 1 minus, so y1 cubed minus 3 over 2 u y1 squared, close bracket. You're integrating from u to 1, right? So then this then becomes just 1 minus an integral, not an integral, open bracket. So 1 minus open bracket, 1 minus 3 over 2 u, close your bracket, minus u cubed minus 3 over 2 u cubed, right? So if you look here, this sub cancels this, right? Minus minus will be a plus, right? So you then left with just 1 minus half u cubed minus 3 over 2 u plus 1, which will then give you just 3 over 2 u minus half u cubed, right? I mean, where your u is an interval between greater than 0 but less than 1, right? So from here, you want to find the density function, right? The goal is to find the density function using the distribution function. So f of u will then be the derivative of the distribution function, derivative of this, right? So it's 3 over 2 minus 3 over 2 u squared, which will then just be 3 over 2. This is 1 minus u squared. And you know that u is between 0 and 1, right? Why is this the case? It's because you're being told y1 um y2 is less than or equals to 0 and 1. And since u is a function of these two variables, then you will need to take the interval of these two variables, where you now have u is just greater or equals to 0 but less than or equals to 1, and 0 elsewhere, right? Now, you also being asked to find the expectation of u, right? So you know the integral of u, the interval of u is just gonna start from 0 to 1. U, right? By definition, f of u du, right? So you try this out, try it out, right? Now, let's look at just the summary of what we've done, what we've learned so far. Right. So the summary of what you've learned is that um so let's look at this summary. Summary is that if you have a function u which is subjective to random variables, and you want to firstly understand the region that you want to where your u is bounded from within your y space, then once you understand the region where u is less than or equals to small u, then this gives you an advantage to find the distribution of u, because the distribution of u is within this region here, right? Which is what they're explaining here. Once we have this guy, then we just need to differentiate f of u to find the density function of u, right? Maybe let's illustrate this a bit further, right? Let's illustrate it. Let's illustrate this, right? So to illustrate, we will consider the case of u being a function of y as y squared, right? We know that f of u, capital letter U, right? This is the same as the probability of y squared less than or equals to u. I mean, we understand that if we want to have y as just a univariate, we need to put the square root on both ends, and the square root of anything is plus or minus, right? So this then becomes minus the square root of u less than or equals to y square root of u, right? So y is greater or equals to minus square root of u, but less than or equals to the square root of u, right? So you have a lower bound and the upper bound, right? So you want to find an integral. So this is a region of u, right? It's from minus the square root of u to the square root of u of f of y dy, right? But what do we know? We know that f of y is just an integral from minus infinity to y, f of t dt, right? This could also be represented as just integration from minus infinity to y, f of y dy, right? So this interval, so keep this in mind, right? So you know this, right? This integral could be split into two. This, I mean, should be split into two. So this is the same as saying an integral from minus infinity to square root of u um, f of y dy minus an integral from minus infinity to now negative of the square root of u f of y dy, right? Now, if you look here, this is the same as this, right? If you look at the structure of what you've just done here, right? So then what does it mean? This is a distribution function of f of square root of u, right? Minus f of minus the square root of u, where u should be greater or equals to 0, because if u is negative, this will be undefined. Now, how do we find small letter f of u? u, which is the density function. It's to do the derivative of the distribution function. So this is a function of the square root of u within u, right? So you need to use partial derivative to find the derivative of the distribution function. So to do that, this then becomes f of, so I use product rule, right? Which will then give me like partial derivatives. So the f of square root of u multiplied by the derivative of square root of u, this is just half um, u minus 1 over 2 uh, then minus f of now the square root of u. Also, you do the same thing. Now you integrate the inner function, which is minus the square root of u, right? So this is half uh, u minus half uh, multiplied by the inner integration of the square root of u, which is the minus part. Then this becomes a plus, right? We know, I mean, maybe let me also say the square root of x is the same as x raised to a half. Okay, right? So this is a density function where u, it needs to be greater than 0, because if u is not greater than 0, this will be undefined and 0 elsewhere. Elsewhere. Right. Let's look at an example. Let's look at an example of this. So an example of this uh what's going on? Let's see. Uh Example of this. Okay, good, perfect, right? So example 6.4, right? So you being told that y have the probability uh density function like this. Now you want to find the density function of u, right? So you want to find the density function of u, y squared. So you know that um you from the previous sort of illustration, you know that if u is like this, right? So that means the density function should be just f of u, u half minus 1 over 2 f of y, the square root of u, plus half u minus 1 over 2 f of y minus the square root of u, and 0 uh, elsewhere, right? Elsewhere. So u is greater or equals to 0. So what does this mean? It means so this should stay the same. Where you see y, you should put square root u. Plus this stays the same. Where you see y, please put minus the square root of u. That will be your density function, right? U should always be greater than 0, but less than or equals to 1, given the interval that everything here should be less than or equals to 1, right? So try this one out. Try it out. Then I have some questions, so please do 6.2 for me. And so this is your tutorials. It should be 6.2, 6.10, then 6.6, and do also 6.3. Okay. Thank you for your time. Have a lovely day. Thank you. Bye.